Hello, Nerea. How are you doing? And Rusty, how are you doing?
Did you hear me?
Little tired, but I'm right. How about you?
I can hear you now, and I can hear Rusty.
Okay. I said I'm good.
Well, good. Oh, man. I was just watching a video about Spain.
What about it?
Well, I was actually watching a video about Football Club Barcelona, but
Oh,
that's about Spain, right?
yes.
I'm a huge fan of Messi.
Me too.
I have to every once in a while I have to go through a binge watch of all of his greatest plays in Barcelona and wherever he's playing. So, do you follow football?
Yeah, well, when I was living here, since I moved over there, I don't really follow it that much.
Yeah. Yeah, I just watched highlights of the championship, the European Championship, where Messi and Barcelona beat Ronaldo and
Mother.
Manchester United. Their first other championship against each other. That was epic. Anyway. All right. Let's see. We'll wait a few minutes and see who else shows up. How are you guys doing on chapter 9? Is the chapter 9 homework coming along for you guys?
I'm still reading the chapter. I haven't started the homework yet.
Well, we're going to do some example problems from the chapter and the homework today. Make sure everybody knows kind of how to do these things. Hello, Angel. How are you?
Good. You?
Very well, very well. What's everybody doing while you're sitting around at home?
Guess I'm essential, so I'm still working.
Where do you work?
Railroad.
Ah, yes. Railroad is essential. Both my sons still go to work. One of my sons works at the hospital, so I guess that's pretty essential. My other son works at Raising Cane's, which I think in Nebraska is considered essential.
We've had a few cases. We've got some people quarantined from the railroad here locally too.
Oh, yeah.
Yeah.
Well, we had somebody in North Platte die the other day.
Yeah, I heard that.
Of course, they were in their 90s. I'm like wondering, did
Yeah.
they die of the virus or did they die because they were in their 90s? When you're in your 90s, everything is fatal to you.
Right.
But not trying to be insensitive, of course, but still.
That's how it is.
Ugh. Ooh. So let's see, we're waiting for Madison, right? Maddie. I think we'll go ahead and get started. I actually I started recording already because keep forgetting to do that. So if she needs to, she can get on and watch the recording later. Are you all seeing my atomic physics textbook here on your screens?
Yeah.
Excellent. Okay, so what I'd like to do is do a quick overview of everything, and if you have any questions, stop me. But then I want to do examples that are in the homework. I want to show you through any of the examples on the homework. So atomic physics is kind of the beginning of quantum mechanics, where we learn about how the atom was first perceived or first guessed at, I guess is a better way to say it. And then we move through till we get to the point where we're treating the atom as it actually behaves according to our observations. And so we start off with this very simple model of the atom that is just a ball of stuff, right? And then eventually they discover that atoms have charges inside of them, and some of those charges can come out. And the charges that come out were the electrons. So they made this model where you have this ball of stuff that is positively charged, and then you have these negatively charged electrons that are kind of poking around inside of it like raisins in a cookie, and they can pop out. And then that's how you get charged things when you rub cat fur on a rubber tire or something. You can imagine how that might happen. But anyway, the chart in this model, the charges are separate so they can come out. And eventually they actually discovered later that even the positive charges can come out, but that wasn't discovered until the early 1900s, when they were discovering things like radiation, because when the positive charges come out of an atom, it's usually because of some high energy radiation from some radioactive source, some radioactive material of some kind. So that and other things, including the Rutherford experiment, where he shot the particles at the gold atoms with the gold foil and watched them bounce back every once in a while, led to this model that we follow more now, which is the Rutherford model. Now, this isn't exactly the model we follow now, but it's very close, much closer than these other two, where the Rutherford model has most of its mass and all of its positive charge at the center of the atom, or at some concentrated point in the atom. And then you have electrons along the outside, around the outside, creating this kind of electric field outside the atom, which gives the atom its size. And most of the atom in Rutherford's model is just empty space. This nucleus, we call it, is actually 1,000 times smaller than the entire atom's space, and so it would be much tinier than this. And this model is very similar to the model that we work with today. During the exploration of the atom and trying to understand the atom, other things were discovered. One of the other things that was discovered is that light also behaves like a particle, just like atoms and electrons and other things, in that light only comes in certain amounts. It comes in like little packages of energy. You can't just choose blue light in whatever energy you want. If you choose this particular kind of blue light, for example, blue light at 450 nanometers, if you're choosing blue light at 450 nanometers, it will only come in certain amounts of energy, and any other amounts of energy will not be found in. It's just not happening. And as they started to study that, they realized that the amount of energy that light comes in is directly related to the frequency, and that there's this factor, this constant that you put in here to make this an equation, and this constant is called Planck's constant, discovered by Max Planck, or Max Planck if you want to say it properly. But anyway, Max Planck, German physicist, he discovered this idea, and they call these little packets of energy particles, and they call them, they're named photons. And when you want to calculate the size of a photon, or the amount of energy that's in a particular photon, you use this equation. The energy equals Planck's constant times the frequency of the light that you're observing. Now, how is this related to atoms? Well, it turns out that one of the experiments that was being done also at that time was they were shining this high energy light, like ultraviolet light and X-rays. They were shining it on metal, and light was coming out, or electrons were coming out of the metal with certain amounts of energy. And when they changed the frequency of the light hitting the metal, sometimes it would not make much difference, but when you got to a certain frequency, sometimes it would make a huge difference in the number of electrons coming out. And so so essentially they were discovering that the electrons inside the atom had energies that correlated with specific frequencies of light, or in other words, specific energies of light. So if you gave the atom just the right amount of energy, then you would get if you gave the metal, the atoms in the metal, a certain amount, just the right amount of energy, then tons and tons of electrons would pop out. And that was because the photons going in had the same exact energy as the electrons had in their binding energies, the energy that holds them into the atoms. So it was just the right amount of energy to kick out those electrons. And it turns out that atoms kick out electrons much more effectively if you give them exactly the same amount of energy as their electrons have. So that is the kind of that connection there. Einstein was the one that explained that and gave rise, or gave a kickstart to this, all of these ideas. And that was called the photoelectric effect, which they talk about here. And the photoelectric effect is used all over the place. Anytime you have something that's detecting light, it takes advantage of the photoelectric effect. And that includes digital cameras, little detectors that detect the light in your garage door, so that if somebody passes through the light beam, it opens or stops closing or whatever. On one side, you'll have a light beam. On the other side, you'll have a detector, that photoelectric detector. And that photoelectric detector is designed to detect a specific frequency of light, or a specific color of light, which happens to be the light that's on the other side. And so if you block that light on the other side, it doesn't matter if there's all kinds of other light coming in, but if you block this particular light, this photocell on the other side will actually not receive the power that it's used to receiving. When it sees this light all the time, the light coming from this one will come over to here, and this photocell actually releases electrons into the wire, and that keeps the garage door opener powered. As soon as this doesn't see that light anymore, then it doesn't power the garage door opener. So if you cut this wire right here, it won't be receiving any electrons from this photocell either, and that will cut off the garage door opener as well. So used all the time in many different safety features and all kinds of things like that in our world today. So here they actually calculate the energy from a photon using the energy equals Planck's constant times the frequency. They do this for a red light, which has a frequency of 5 × 10⁻⁴ hertz. That's not the only color red that has that frequency. Many frequencies that are very close to this also look red. So you can pick 5.1 or 5.01, or even probably, I don't know exactly what the range is going to be, but it's anything that's close to this frequency is going to be red. And we'll have this particular frequency, 5 times 5.00 times 10⁻⁴, has photons. Each photon has 3.32 times 10⁻⁻19 joules. So you could have one photon that size, or you could have two. And in that case, you would have 6.64 times 10⁻⁻19 joules, because you'd have two of these. That'd be the total amount of energy that you had in that light. And if you had 6 million of these, you would multiply this number by 6 million. Or if you had 532,655,738,231 of these photons, then you would take that number and multiply by this number to get the total amount of energy. But you could never get 2.5 of these for this frequency, because the energy in photons, the energy in this particular frequency of light comes in these photons, these packages of energy. And that's why they call them particles. Even though they have no mass or matter involved, they're still particles in that they are specific size packets, specific chunks of energy. And so we call this idea that light has this particle nature to it, we call it the particle the wave particle duality of light, because light still behaves like a wave, but when we're looking at it as it interacts with things like atoms and other particles, it behaves like a particle. So this is that great example where if you're treating light like a wave, then you can just spray waves onto something, like water is sprayed on a fire to put it out. But if you're treating light like a particle, you have to throw water on in buckets. You can throw one bucket on, then two buckets on, but you couldn't just pour it out of the bucket. This isn't the greatest analogy, because when you're dealing with light in different ways, when you're dealing with it as a wave, you don't do the same thing with it that you do when you deal with light as a particle. When you're dealing with light as a wave, usually what you're doing is things like focusing it through lenses or bouncing it off mirrors, or you're using a telescope to look at stars far away, or you're looking at a microscope, using a microscope to look at something very small. And that's when you treat it like a wave. That's when light behaves like a wave. But light behaves like a particle when you're doing something else with it, which is usually when you're shining it on something like metal, watching electrons pop out, or if you're shining it on an atom to change the energy levels of the electrons in the atom, or things like that. So that's where this analogy kind of breaks down. Okay, so here's just another tribute to Albert Einstein, who gave Einstein just about every new science that has happened since 1900 has had something to do with Einstein's theories or Einstein's papers. Einstein wrote 5 papers in 1905. One of them was about the photoelectric effect, and the other 4 were all about relativity. And all of these papers were so broad reaching, they had such an incredible scope to them, that they pretty much gave rise. I mean, it's very difficult to find any new science or math in the past 100 years that is not affected in some way by those 5 papers. In fact, I don't think I've ever even come across one. I just don't think there is. There's not, I mean, even in things like biology, it's just not happening, because everything that's happened in every field of science since then has taken advantage of those discoveries in some way or another, pretty much. So it's kind of crazy how much impact he had. And it wasn't just accident and providence and some, goofy alignment of the stars. He truly was one of the most brilliant people who ever lived in the human race. And I mean, you could maybe in the entire history of man find 50 people among the billions that were even remotely like him. So anyway, so the last theory of the atom that we cover in this book is the Bohr theory, which Bohr came along a couple decades after Rutherford. Rutherford was kind of turn of the 20th century, 19th, 20th century. And Bohr was early, mid 20th century, in the 30s-ish. I want to say it was pre-World War II for the most part. But that was kind of his high point. But this model came about in the early 1900s. It says here 1913, so it was pre-World War I. And Niels Bohr was Danish, and he was studying atoms as you shine light through them. So the experiments that he was doing were experiments like this, where you have a white light source and you put it through. This is like the experiment we did. You put it through a prism and you make the rainbow, right? But what he was doing is he was using instead of a white light source that has all kinds of wavelengths in it, he was using what's called a gas arc tube, where you have a tube full of gas, and then you have electrodes on each end, and you put lots of voltage across it, and you get this little lightning bolt that goes through the gas. And what that does is it's using the electrons in the gas are jumping from atom to atom to atom, you could think of it as. And so the electrons are jumping out of the atoms. and they jump out at specific energies, so they only give off specific frequencies. Well, they were trying to explain this, and one of those explanations is that idea of the light particle wave duality, wave particle duality of light, but also it had to do with electrons. So it has to do with electrons being having certain energy levels inside the atom. So he learned that in hydrogen, for example, there are these four energies that are associated with these frequencies of light, and these are actually not the frequencies, but the wavelengths. So, but the wavelengths related to the frequency, of course. So you have the wavelength of 410, you have it 434, 486, and 656, and these are the four visible light that he saw come out. Instead of splitting and becoming a rainbow, he just saw one little strip of, or sorry, two little strips of purple a little bit far apart here, one that was kind of a turquoisey, greenish blue, and then one over here in the red. And he discussed, and what he was able to say is that um, the electrons inside the atom only have specific energies. They can't be in between these energies anywhere. And that kind of threw a lot of dirt on Rutherford's theory. Rutherford's theory can kind of explain this as like a sun with a bunch of planets going around it. Well, when there are planets going around a sun, they can be anywhere they want, and they can have any energy they want. The only thing that determines their energy is where their orbit is, essentially how far their orbit is from the sun. And Rutherford just assumed that the electrons could be any distance from the nucleus and have any energy they wanted. But here, Bohr was showing that they could only have certain energies, which, if they were going around in circles, would suggest that the orbits there were only certain orbits allowed. In other words, you could only be this far away from the nucleus, or this far away, or this far away, which didn't make sense classically. That didn't make sense according to Newton's theories and all the other theories about orbiting planets. And so apparently atoms don't obey the laws of orbiting planets. Another experiment that he did, Niels Bohr was doing, and others, was that they took white light and they shined it through a tube of just cold gas, and they got a very similar thing where light was absorbed at those same exact frequencies. Instead, they got the entire rainbow except where those frequencies were before. And this actually showed that the energy was being taken by the electrons and being essentially used by the electrons in this gas. So an electron would absorb this certain amount of energy because they were in that particular energy, and the electron would then be kicked up to a higher level, or would, whatever the electron did with that energy, neither here nor there at that point. But it was definitely absorbing energy or emitting energy, releasing energy at specific frequencies, which led to this new idea of the model, which is the Bohr model. Now, the new idea of this is not really a new idea of the construction of the model. This is essentially the same as the Rutherford idea, where you have a nucleus at the center and you have electrons on the outside. The only real difference between this one is how the electron orbits are organized and how electrons behave between them, where they can be in one orbit or another orbit, but they can't be anywhere in between. And that includes traveling in between. That means that you have this quantum leap, as they call it, and you've maybe heard that term before, between these energy levels. And they give numbers to these energy levels. The lowest, or the what you could think of as the closest, even though it's not necessarily related to distance, because we have no evidence of that. But anyway, this most tightly bound, or we often call it the lowest energy level, or we often call this one the ground state. Often we call that. Anyway, the point is that this energy level that is down here near the nucleus is what we call n=1, and it has the lowest energy level, even though it requires the biggest amount of energy to get it out. Why do we call it the lowest energy level? It's because the energies that are associated with this atom are negative energies. So the lower one has the biggest negative energy, and that's because it's a binding energy. It's kind of like a potential energy. It's the energy it could have if you released it from the atom, and it's the energy, that's the amount of energy that is held in that binding force that holds the electrons in here. So that's the n=1 state, or sometimes called the ground state. And then n=2 state is the next one out, then n=3, and n=4, and n=5. And all the way up to n=infinity, really, at n=infinity, the electron is considered free. It's not considered bound to the atom anymore. But the interesting thing about these energy levels is they get closer and closer together the further you go out. This doesn't really show that very well. But this one, the distance in energy between this level and this level, n=1 and n=2, and then the difference between n=2 and n=3 is very, very different. And they show that down here at the bottom of the page, where it's difficult to really give you a graphical representation of these energy levels without more mathematics involved. But this is a fairly good one. So if you imagine the nucleus to be down here, and each one of these things here to be the different states, or we call these excited states, then n=1 would be down here very close to the nucleus. And if it was an orbit that actually went around the atom, it would be a very small orbit. And if it was an orbit, it would be going very, very fast around. But it's not any of those things. And people always ask me, well, how do you know it's not any of those things? Well, how do you know that it is? By observing it. And we've never been able to actually look at the electron going around the atom or anything like that. It's too small to see physically. It's just impossible to actually see. So, and there's plenty of evidence that suggests that it's not going around. And anyway, the point is that the next available place where this electron can actually be is this far away. This bottom one is -13.6, the next one's -3.4, and then after that it's -1.51. So the distance between this one and this one is more than 10 electron volts, and the distance between this one and this one is 1, or 2 electron volts ish. So it's a major difference, and they get closer and closer and closer together until they essentially get infinitely close together, and you can't tell the difference between one state and the other because they're so infinitely close together. And that's where the electron is free to just move around between states because there's no energy difference, and then it's free to just leave because there's no energy difference. It's so close to a zero energy. Once you get it to a zero energy, the electron is not really bound to the atom, and it's not really bound to anything. It's just kind of floating around out there, and there are a lot of electrons doing that in the universe. So. Okay. So some of the math that comes out of this is shown here, and kind of. Oh, there, yeah, it's right there. Sorry, I missed it. Okay, so here one of the things that Bohr was able to calculate is the Bohr radius. So this would be the size of the atom if we consider the atom to have orbiting electrons, like electrons that are going around and around and around. Why do we keep saying that? Why do we keep considering that if they're not doing that? Well, because there are some ways that it does kind of work and some ways that it doesn't. So the science of quantum mechanics is very difficult to do, because there are so many things that seem to make sense according to our classical understanding of physics, and then at the same exact time those same things seem to not make sense in some other way, and maybe even the same way that they did make sense. It's so confusing and so difficult. And I've often likened to this, and I think I've probably talked to you guys about this. I liken this to playing a pinball game, where you cover up and you paint the top of the pinball machine, and maybe you can only see the edges or see the lights going off, and you're trying to play this game with this secondhand information about what's actually going on. And and not only that, it was a hard game to play to begin with. So it's and trying to make guesses from the reactions of the game or the reactions of the controls. That's exactly how it is with quantum mechanics, except infinitely more diverse and complicated and complex. They're just throwing things like electrons at atoms or other atoms at other atoms and looking at what happens to their instruments, because they can't actually see what happens to the atoms. but they look at what happens to their instruments, to their scientific tools, and they try to make logical conclusions of what that means. And they make a logical conclusion, and then they test that 1,000 different ways, and they find 500 ways that it makes sense what they thought, and then 500 ways that it doesn't make sense what they thought. So they have to think of another thing to do to try to flesh out the problems there, and another thing. And they're constantly creating these ideas that try to describe what they're seeing, and then they test those ideas to see if they're working. And it's an incredibly creative process, because you have to create from so little. You have to create something from so little evidence. And it's an incredibly frustrating process, because there are so many things that can go right and so many things that can go wrong with the same thing. And then you have to try to sort those things out. I maintain that there's probably nobody in the history of man who is more creative than these particle physicists have been over the past 100 years in trying to figure things out like this. I think they're the most creative people the earth has ever seen, including all artists and musicians and whatever else. I can't imagine anybody being more creative than these people have been, from my education in these things and my research in these things. It's really quite amazing. So anyway, so the first thing that we can do is we can calculate that Bohr radius. And the way that we calculate the Bohr radius for hydrogen, this really works best for hydrogen. And which is kind of funny, because it's the most simple atom, but once you get into other bigger atoms, it starts to become much more complex. This works fairly well for most atoms, but it still works best for hydrogen. Where you take this number 0.053, which we call this is actually called the Bohr radius. Just this 0.053 is called the Bohr radius. But the Bohr radius of an atom is the Bohr radius 0.053 times the principal quantum number where the electron is at that time. So if the electron is in that lowest state, which is n equals 1, then the Bohr radius is just 0.053, because 1 squared is just 1. But if you're in the second state, n equals 2, then you square 2 and you get 4. You have 4 times 0.053, which ends up being 2 nanometers instead of not 2 nanometers, ends up being 0.2 nanometers. So that's a fifth of a nanometer. So it becomes 4 times bigger in its radius instead of 2 times bigger in its radius. And if you put in 3, it becomes 9 times bigger. So the further the less energy your electron has, or the higher state that it's in, you get a much, much bigger atom, essentially. The atom becomes much bigger because
Does that number only apply to hydrogen, or is that for everything?
This works best for hydrogen. There's another series of formulas that works better for bigger atoms. It works best for hydrogen, though.
But it's all 0.053 for other things as well?
This number is included in other things, but there's other things that happen with the N with other atoms. So you can use this for everything that we do in this book. It turns out that most atoms are about the same size. They're all about in this kind of really tiny range. They range from the smallest at 0.053 to the biggest not being much bigger than a nanometer, maybe at the biggest. I don't think the biggest one's even that big. So there's this range that is between a half of a tenth of a nanometer to about maybe half a nanometer to a nanometer-ish, somewhere in that range. They're all in that kind of range. It'd be like saying all atoms are the size of a tennis ball at smallest to the size of one of those big balls that you can climb inside of and go rolling around on a gym floor playing some game in or something, like the big hamster ball for humans. So all atoms are in this range, kind of about that range. That's not that big of a range, even though it seems like it when you blow it up that big. But atoms are all pretty close to size for each other. It's not like one atom is like a tennis ball and the other one's like the planet Earth. A factor of 100 is about as big as it gets. So anyway, they actually calculate this. So they calculate the radius for n equals 1, and that's an obvious one. But the other equation that comes out of Bohr's theory is the energy level equation, where you can calculate the different energy levels for the different quantum numbers. Now, this n number is like what we call the principal quantum number. It was the first quantum number really discovered, and quantum mechanics comes from this idea that the energy levels have certain energies, that light at different frequencies has certain packets that it comes in, that atoms have particles inside of them that are specific particles. The atom is not just this ball of goo. The atom is actually quantized particles. There are different quantifiable things inside of there. So that's the idea that quantum theory all comes from. So if you want to calculate the energy level, you take negative 13.6 electron volts and divide it by n squared. And they calculate the n equals 1 ground state of the hydrogen atom. And that, of course, is very obvious. They do the very obvious ones because these are very simple formulas. Of course, if you plug in n equals 2 into here, you're going to get negative 13.6 divided by 2 squared, which is negative 13.6 divided by 4, which is going to give you something like 3 point something. So whatever it was in the 3.4, or yeah, 3.4. So you're going to get negative 3.4 electron volts, which is much, much different than 13.6, right? And if you put in n equals 3, you get 13.6 divided by 9, which gives you 1 point whatever. And the change is very, very different as it goes up. Now, one thing that we didn't cover up to this point, some of the things that we haven't covered at all up to this point start here. We didn't get to this part, but we've talked about it, where atoms emit photons of energy, photons of light, when electrons jump from one state to another state. And this equation describes that process, where you have the energy in a final state and the energy in initial state. And if you take the energy in the initial state and subtract the energy of the final state, you'll get the energy of the photon that comes out of that atom. So this goes back to that experiment that Bohr was doing when he was putting electricity through the gas, and then he was putting the light that was coming out through the prism, and he saw just those particular lines of light. Well, if you use this equation combined with this equation, you calculate your energy in state 2 and your energy in state 1, for example, and then you take the energy of state 2 where it starts, and then you subtract off the energy from state 1 where it finishes off. So this would give you the energy of the photon if the electron jumps from n equals 2 state to n equals 1 state, which would be a situation where an atom would release some light, particular, and that'll calculate that energy that's released for those states. So this is essentially what's happening. If you have an electron this is called an excited electron, or an electron in an excited state. Whenever the electron is in the lowest possible state, or the closest possible state to the nucleus, if you want to think of it in terms of that classical orbit, it's called an excited electron whenever it's in any state above this ground state. And excited electrons always have this natural desire to be in a lower state that's empty. So if there's a state below them that's empty, they want to drop down to that state. When they do, they lose energy. And then energy leaves the atom in the form of an emitted photon. So you get some light out, in other words. And that light comes out in a specific amount of energy, a specific packet of energy, because it is a photon. So that's a transition from an excited state to a lower state. In this case, n equals 2 to n equals 1, where n equals 1 is the ground state. But you can have the exact opposite thing happen, where you have an electron in a state of the atom. It doesn't have to be in the ground state. In this case, it is. But you have an electron in some state, and the n equals 1 here, and a particular photon of light comes in, and it will jump up to the next state. But it will only jump up if this photon coming in is exactly the amount of energy that is required or that is the difference between this state and this state. So if this is the ground state and this is n equals 1 in hydrogen, the difference between those states is 13.6 minus 3.4, which is 10.2. This photon coming in has to be 10.2 electron volts in order for that electron to make that jump. If it's not, it won't make that jump. It will just sit where it is. So that's, and that is the explanation of why certain types of light shining on metal allow electrons to come out of the metal, whereas other frequencies of light didn't, because you have to get that frequency just right to knock those electrons out from particular states. So here is the complete spectrum from n equals 1 up all the way up to n equals 5, it looks like, ish. Well, these are all the transitions down that end at n equals 1, n equals 2, and n equals 3, it looks like. And they actually, they give them names. The one that we saw earlier in the book was this one here, where you have that red light and that turquoise light and the two kind of purpley lights. Those, they were able to discover that those transitions, or those photons that came out, resulted from electrons that fell down from the n equals 3 state to the n equals 2 state, or the n equals 4 state to the n equals 2 state, or the n equals 5 state to the n equals 2 state, or the n equals 6 state to the n equals 2 state. So in other words, a bunch of transitions that ended at the n equals 2 state. Those give you just the right amount of energy so that it creates light that we see, the red, the turquoise, and the purples. Anything that falls down from above the ground state to the ground state creates a much higher energy light. And these ones are, we call these the Lyman series, but they're all light, they're all frequencies of light we can't see. They're in the kind of the deep ultraviolet light. So we have the higher energy lights, much bigger jumps, so it's a much bigger energy, so it's a much higher frequency light, and it's outside of our visible range. In order to detect these, you need to have ultraviolet, some kind of ultraviolet detection method. When you get up higher into the higher quantum numbers, and you drop down to like n equals 3 or n equals 4, n equals 5, anytime you jump between states up here, it's a very small jump. So it's a very small change in energy. So the amount of light released is a very small amount of energy also, which means it has a very small frequency, a very low frequency of light. That means essentially just low energy photons, and you get things like infrared and microwaves and radio waves out here, and which is also difficult to see because our eyes can't detect it. However, a couple of advantages with these low energy, these low energy things like the infrared and the microwaves are some up in here, and radio waves are somewhere up in here. The advantages of those waves being very low in frequency is that they travel very long distances, and without being kind of messed up, and they're not dangerous to the human body. These ones over here are dangerous to the human body, so when you start observing them and doing science with them, it's kind of hazardous to the scientist's health. These ones not so much. So not at all, really. Also, these ones over here tend to be easier to detect in other ways besides just looking at them, since we can't look at them. But many sciences use the waves that are made by atoms out here for detecting. In fact, recently, just last year, something really cool happened in the physics world. Somebody was able to take radio telescopes. All the information comes from radio telescopes. What a radio telescope is a big telescope that instead of looking at visible light, it looks at radio waves. So they look like big radar dishes for the most part. And usually it's not just one. When you have a radio telescope, you usually have many. So this one right here is called the Very Large Array, and it's in New Mexico. and it's the biggest one in the world and has been for some time. It's on all of these radio telescopes are on railroad tracks, and the railroad, they can move these things out a super long distance. Let me see if we can find, here we go. So out here in the very large array, you have these railroad tracks here. You can put these things onto the railroad track, and you can move them out into the desert. And I think they can move out something like, I don't know, a couple of miles in every direction. It's so big. You can see it bigger, see how far it goes out there. It's a long way out there. Might even be a few miles. But anyway, the further they put them apart, the deeper they can look into space with them. And these are not the only ones out there. There are many other radio telescopes out there that are also very large. And the biggest single radio telescope is Arecibo, which is in Puerto Rico, I think. And it has this big bowl radio telescope in this little valley. It's just insanely huge. Oh, that's a cool picture. Anyway, what they're doing though with these is they're detecting radio signals from atoms inside of stars and planets very far away, mostly stars. And as these radio waves travel through space, because they're very long wavelength, they travel a very long distance without being distorted. And so you can see what's happening in a star, you can see what's happening in space. And they actually used these they used information from radio telescopes all over the world to actually make an image of a black hole, the first one ever. And here it is. What you're seeing here, the bright light here are radio waves from the edge of the black hole. And what a black hole is essentially, it's a star that got so big that it collapsed on itself. In other words, it's the gravity from the star itself became so strong that it actually sucked itself into a tiny little ball. And so it went from something like 1 billion times the size of our sun to something the size of something smaller than the Earth, but it still has all the same amount of mass. So it's extremely dense. And the gravitational pull, when you get close to that very, very dense planet, becomes so strong that it sucks everything near it into it, including light. Light can't even get out of it. But around the edge of it, there's this place called the event horizon. And the event horizon is where things are kind of rotating around, kind of like in a toilet bowl, and they're about to fall into the black hole, but they haven't fallen in yet. And as they're rotating around, they're emitting all kinds of radio waves. The atoms on these things are emitting all kinds of radio waves. And those radio waves are flying out into space before the stuff falls into the black hole. And of course, where the black hole is, nothing comes out of that. You can't really see anything. And that's what this image is here. This right here is what they call the accretion disk, and the event horizon is the line between, that line between the dark spot and the bright spot. And then you have these kind of jets going off the side, which is what they call the relativistic jet. That's particles that come in super close, but are going so fast by the time they get in here that they actually, instead of falling into the black hole, they just get accelerated and get shot off into space at relativistic speeds. It's kind of like slingshotting around a planet or something like that. So this is the first image that we've ever made of a black hole, and was made last year. Really exciting stuff for science nerds like myself. So anyway, all right. But that's what they're observing, are these radio waves coming out of those atoms going around and around that black hole. Here they calculate the size of a photon going from n equals 2 to n equals 1 in hydrogen, using that equation we just talked about. And that takes us really to the end. They talk about here, in this section, they talk about some of the applications of these sciences, making microwaves and X-rays and things like this. This all comes through these ideas of light coming from atoms at specific wavelengths. Lasers are another great application of this idea, where we can take advantage of these particular energy levels in lasers. The MRI, the CAT scan are all come from this idea. So this nothing else to calculate here. Here they talk about how lasers work, where they put in a specific frequency to excite the electron from one specific level to another specific level. But when you're doing this with lasers, you're picking a particular atom, not usually hydrogen, but it's usually a particular atom where if you put in this light, the electron will jump up to another level, but it will immediately come back down to the previous level. When it does, it actually releases two of these things because of you have the photon coming in and the photon coming out, and it stimulates essentially the photon coming out actually causes the next atom to do the same thing, and the next atom, the next atom. It's kind of like a chain, kind of like a chain reaction. It's less of a chain reaction, it's more like what they call a cascading effect. So this thing grows bigger and bigger very rapidly, and that's why they call a laser. Laser is called light amplification. That's this part. Stimulated emission of radiation. So laser stands for light amplification of stimulated emission by stimulated emission of radiation. So anyway, here they give another example of how that works, where you have these electrons down here. You give them a certain amount of energy, and all these electrons jump up to that higher level, and they stay up there as you're giving them this energy until you give them just the certain type of energy, and then they start to jump up and down. They essentially bounce back and forth. And as they're bouncing back and forth, they're releasing tons of these energies that are all the same. So they all have, that's why lasers are all one color, and that's why they're easy to focus, because they all have the same wave coming out. And not only are they the same wave, but the waves are all in sync with each other. In other words, all the peaks are lined up so that it's a very, very bright light and very, very organized, very easy to work with. Sorry, we're going a little bit over time here, but yeah, here they talk about Heisenberg's uncertainty principle, which really, I don't know if I gave you anything like that. Okay, so this last thing here is actually, this is the kind of the polar opposite of the particle wave duality of light, which is the particle wave duality of matter. It turns out that even matter can behave like a wave, where we normally think that matter behaves like a particle. It's not necessarily easy to explain how matter behaves like a wave. But suffice it to say that if you shine electrons through, if you bombard the equivalent of a prism for electrons with electrons, you'll get diffraction patterns just like you do with light. So they show these patterns that only exist if things are behaving like waves. So very, very small particles can behave like waves. It doesn't necessarily mean that they become waves, and it doesn't necessarily mean that they're like light or like anything like that. They're not. They're not like sound waves or anything like that. And that's unfortunately what most students get from this idea of this. This is an idea that was suggested by a guy named de Broglie. But to determine the wave of a particle of matter, you use this equation that includes Planck's constant again, where the wavelength of the matter is equal to Planck's constant divided by the mass of the particle and times the velocity or the speed of the particle. So it depends on how fast the particle is moving and how massive it is. It needs to have a very small mass and a very, very fast speed combined. Well, I guess the speed doesn't matter so much. The wavelength actually will be there if it's going fast or slow. But you need a very, very small particle in the end for this to work. So if you have a very, very small particle and you put it into this equation, you will get wavelengths that are kind of the same size as the particle. So this is for an electron that's moving pretty fast. It has about a 1 nanometer wavelength, which is about the size, of, I mean, it's not about the size of an electron, it's about the size of an atom. Remember, 1 nanometer was the largest kind of size of an atom. So this electron has a wave that's, reasonably close to the size of an atom. If you slow electrons down, those waves become, this number down here becomes smaller and that wave becomes bigger. But how do we make use of those? Well, what we do is we shoot electrons at things that are very small and watch how they diffract off of them, watch how they move around them, in other words, and then we can make images of that diffraction pattern. And so this is looking at blood cells, for example. You can look at blood cells with, is that the white blood cells? Yeah, there's the white blood cells and these are the red blood cells through an electron microscope, which is very difficult to see otherwise. It's very difficult to see with a visible microscope. So you can, and using electrons, you can get a much better detection of very, very small things. It's not really an image. It's not like you're seeing this with your eyes. It's that the electrons are diffracting off of it, and then we use that diffraction to make an image using a computer. All right. And then they talk about the final model of the atom using math that you don't ever need to know anything about. And this is the idea that these electrons going around, there's, quote unquote, going around atoms are actually not going around. They're actually creating these standing waves around the atom. And if those standing waves aren't exactly the right, they don't match up exactly right, they can't work. And that's just another way of thinking about the atom, but it doesn't really change anything that we've done so far. They talk about a bunch of stuff in here that you don't want to know really, and I don't really want to try to explain without the mathematics. And I didn't ask you any questions about it really, so it's fine. Excuse me. So the homework, I can't remember what I made it do. I think maybe I made it due tomorrow night. Does that sound right? Okay.
Yeah, that's right.
So we didn't get a chance to get to all the homework because I forgot that we had a couple sections at an end that we didn't cover. But what we'll do is we'll turn you loose on the homework and just send me any emails that you have, questions that you have about the homework before tomorrow, and we'll get them answered up. And if we have to cover something on Friday, we will. If not, we'll just start chapter 10 on Friday. Sound good?
Yeah. Do we have lab tomorrow? Do you have to connect, or you're sending?
No, we won't have anything tomorrow.
Okay.
No, nothing at all tomorrow. All right.
Okay.
Okay.
Have a good
Will
one.
you be sending us?
Sorry,
Will you
go
be
ahead.
sending us, like lab
Nope.
for tomorrow?
Nope. No lab.
Okay. Alrighty.
We'll do a lab during the chemistry sections, and that will be the next lab that we do.
Okay. Thank
Have a
you.
good one.
You
too.
You,
Bye.
you too.